Well, good morning, everybody. For those who don't know, I'm Chris Jones, GM at Vicom, and I'd like to thank you for joining us today on another of our series of technology training webinars, this time on Wavelength Division Multiplexing. So VIAVI Solutions and Vicom, as a VIAVI Elite partner in Australia and New Zealand, are working closely together to bring this webinar to you. And now I'd like to introduce you to our presenter, Matthew Zara, who's Regional Product Line Manager APAC for Converged Instruments and Virtual Test at VIAVI Solutions. Matt's an experienced test and measurement engineer who's been with VIAVI for over 5 years. Over to you, Matt.
Thanks, Chris, and good morning, everyone. It's good to have you here, nice and early for the Australian ones, and okay and early as well, I guess, for the people from New Zealand. So let's get into this. I'm gonna switch off the video so we can focus on the presentation, but I just thought to say hello in person. So, okay, so today we're going to discuss how Dwdm is changing the world of access networks. And I know that most of you will probably be very familiar with Dwdm in the different parts of telco networks. So we'll talk a little bit about that, but the main focus will be on how this is now transitioning or feeding into the access networks to make them stronger and more scalable as well. So before I get into that, I like to introduce a little bit the company I work for, VIAVI. So for those of you, perhaps you know us through the different names we have had in the past, a very long and rich history. So VIAVI as a company has been going on since around 1923, and it went through the motion of time and evolved together with the technology we support. So today we're in most countries around the world, supporting all the different type of networks and architectures that are used in today's communication technologies. But also we are part of the newer trends of optical security and performance in the way of you probably have us on your phone as well with the 3D sensing. If you have an Apple or a new Samsung and it recognizes your face, for instance, that is also our patented technology that we develop. And VIAVI has around 2,100, I believe, patents. So we invest heavily in our R&D to keep innovating. And this brings us to the leadership that we have today in the market. So we have a lot of number ones in the way we lead the market. So into the fiber, metro, enterprise, into the 5G, wireless and avionics, and also, as I mentioned, into the security. So today, although we cover all of these products, we're going to be focusing on a very niche area of what VIAVI supports. So coming back to our webinar, so some things I would like to achieve as an outcome, some learning objectives is, firstly, we'll go through understand why Wdm technologies are used, and some of the more popular ones, especially in the region. So different parts of the world tends to have a different flavor, but there's some common ones which we will discuss today, and Dwdm will be one in particular. And then we can talk a little bit about the implementation and how to install and maintain the Dwdm networks, and we'll go through some best practices of what needs to be looked out for. And then we'll go through some of the challenges that we have learned so far from our customers and how we have innovated some of our products to help them jump over those obstacles. And yeah, we'll have a good understanding at the end of this of what it is involved and how you can qualify a good install of a DWDM network. So first of all, WDM, wave division multiplexing, what it basically does is, firstly, it's an optical multiplex technology, of course, and it's used to increase the bandwidth over an existing fiber, right? So what we do here, as you can see, we combine transmit multiple signals simultaneously, all at different wavelengths. Here we see them as different colors, and these are all transmitted on the same fiber, right? So you can think of this as perhaps you have virtual fibers, okay? So you have you can multiply the capacity of that same physical fiber medium with the number of virtual, they're called channels. So the more channels you add in those different wavelengths, the more the capacity will increase, okay? So what does this do? Of course, this helps different operators drive down the cost per kilometer, and it is the trick to a scalable network that operators use. So think about if we develop, or if 100 gigabit per second service is run on every channel, or maybe 400, or even, you know, there's elements of 1 terabit now on the cards. So if you have multiple lanes or multiple channels of this, you can see how quickly that capacity can be multiplied. All right, so there are different WDM standards. So the two perhaps most unpopular nowadays are your CWDM and your DWDM. So, you know, there's different uses for the different technologies, and there's always a balance between cost and distance here, for instance, and complexity of a network architecture. So if we change this into a little bit more of a graphic, you can see, for instance, a wideband WDM channel would be spaced in 100 plus nanometers apart, okay? And here we can see one, for instance, in the O band and another one in the C band, right? And this is similar to some perhaps common networks like PON, for instance, where you have 1310 going on the upstream and you have 1490, for instance, going on the downstream, okay? However, that causes limitations, of course, in terms of they use a lot of the wavelength allocation, so you can't really have that many channels included. If we look at the CWDM, you can start seeing with the coarse WDM, you know, you can push in 8 or 18 now more channels, okay, into the same wavelength allocation. So there you can add more capacity. And if we look at the DWDM, so here we're showing a 96 plus DWDM. I believe the maximum at the moment is 196. But for the reason of this webinar, we'll talk about these 96 ones. So you can see in such a narrow, in just the C band, right? In a narrow wavelength there, we can push in 96 plus channels of capacity in a very narrow wavelength. So the way to do that is to densify, to use special lasers which are more precise and they have a better resolution and they can be sharper in the way they operate. And so you can pack together these channels, and the spacing is extremely narrow. So here we're talking about 0.4 to 0.8 nanometers apart, okay? So typically those will be, I'll go a slide back, in the 50 gig to 100 gigahertz type spacing, okay? Okay, so So why is DWDM again used into these fiber, and how is it being now leveraged off into the access network? So again, onto the access side, there is more need for bandwidth. Now, operators can choose to, of course, run more fiber and divide the time allocation per user with less users, but that will be very expensive. So that doesn't change the fact that there's this positive trend for more bandwidth, and it doesn't seem like it's going to be changing anytime soon. So what happens is, even from traditional type networks, technologies like HFC and copper and DSL, there is a requirement also for fiber deep. So this fiber deep now is pushing the demand for that same fiber that is coming from the core into the metro into the distribution to feed more fibers on the access. So again, would you have to run different distribution fibers, or would you be running those virtual fiber channels that we spoke about? Okay, so if we use the DWDM into the access fiber, this will allow us to increase the capacity, and therefore that will reduce all sorts of costs involved. So this will allow more and more capacity into the different technologies, whatever it is at the customer side. Okay, one very good advantage also of WDM with the components that it uses is that most of them are passive, so they don't require any power, or there is less disruption, if I may, caused by different things that can happen, basically. So let's dig into this a little bit more on the usage. So you're probably very familiar with the use of DWDM in the core, in the long haul, where today, very popular 100 gig, and also getting to now 400 gig, and this allows the different paths between different areas of a region, and then going from that core, we have other ring networks of DWDM feeding the different areas of a metro network. Okay, and again, 100 gig, very popular nowadays. And as we go further left, these metro networks then start feeding into those fringe networks, like your distribution hub, feeding into the different areas of the metro as well. So this is the evolution here, as we see, of DWDM. So as you can see on the footnote there, the DWDM type technology has been implemented into the network since the early 2000s. And I think around 10 years ago, it started getting very heavily invested into the metro. And only now we're seeing this technology popping up into the different areas of access. So I want to discuss a little bit more what we mean by access. Here, for instance, we see a 4G, 5G mobile base station. And here we have a color code. So that means that this distribution hub has this multiplexer. So it's feeding different wavelengths into this access hub here. And then from this component, which is a demultiplexer, it can separate a wavelength that will feed the mobile base station, but it will allow the other wavelengths to get into a business, or maybe it could be a single wavelength, could be multiple. So over here we can have other streams depending on what we want to feed. So all of these components at the end of the day, they are running on the same single fiber back into the distribution hub. If we talk about 4G, 5G architectures, this is allowing a lot of expansion as well, and it's utilizing again the same fibers that are existing in the ground today. And there are multiplexers and demultiplexers being connected on the ends of them. And what happens is those demultiplexers then can have different spares, different ports, which drive the different wavelengths out into your different areas of the 5G. So as we know, 5G is a technology that is going through densification of base stations. And you can imagine the cost if we had to, or if operators had to run all of these new fibers back into a very far distribution hub. So using Dwdm here for the backhaul, for the mid-haul, allows, and even for the front haul, allows that OpEx to be reduced. Okay. Now, one other use of Dwdm actually coming into play. We've seen this being developed this year. So there is evolution in the PON networks. So what we see is this one here, that super PON. So it's being developed by Google is a very big investor in it. They are developing a type of PON that also can be run over Dwdm for the same reasons. Okay, so now we're talking about 1 gig, 10 gig into the customer premises, and this poses a big problem if we had to supply all that capacity per user. It will be an unbelievable amount of capacity to run on this sort of technology, right? So if we didn't have Dwdm densification, I can't think of our world, we live in today with Web 2.0, the density we have in the cloud, for instance, cloud computing, so none of this would be possible. And Google here, they're already looking at this future architecture on how they can feed more users on that same fiber as well. And the way it's being designed is to have multiple OLTs, of course, because you still need an end capacity management component. So all of these will feed that Dwdm multiplexer inside the hub, or inside the CO, sorry, and then that will be transmitted to different hubs, which will then feed into the different splitters, and then those splitters feed into the different users. Another use is the HFC world. I think I mentioned it before, and there's a lot of HFC operators now looking into what's called DAA, or distributed access architecture. So basically what DAA does is it pushes out the HFC or the coax component closer to the, or it limits it closer to the last mile, if I may use that. And so, of course, fiber gets closer, and then you have components like the RFI or RMEC-PHY type DUs, which convert the fiber back into DOCSIS, for instance. So these boxes, of course, need to be driven by light, and if you had to run again a fiber for every box, it will be a very very expensive task. So running different wavelengths into the different boxes allows for that technology to scale as well. So these are all different types of access technologies, right, that are either today leveraging of DWDM or are set to take advantage of this technology. Okay, and here again is the example I just mentioned of the DIA architecture. Okay, so this is also a study being done by NBN, for instance, in Australia. In New Zealand, Vodafone, I believe they already have gone through the RFI node as well. So this is actually technology that is being utilized in the region or in our countries by the operators. Now, DWDM is very beneficial, but it also comes with its own little bit of challenges. So when we have multiple wavelengths at play, we have to look into what can happen if those wavelengths perhaps don't stick to their position in the spectrum, or if there are any other issues with power level. You know, in the core, you'd have to look at the power levels as well, if it's going to overwhelm amplifiers, you know, if you have some of these channels being turned on or off. You also have different technologies sometimes on the same fiber. So we've seen, for instance, in Korea, there's a mix of DWDM and CWDM. There's also DWDM being used on all their CWDM networks. So that adds to the complexity. O-band and core wave, we don't have, I haven't come across these in the region, but there are also different technologies used in different parts of the world as well. You have a challenge here where you have also an entire system which is live, and this comes live once the first wavelength is turned up. So if you have, we spoke about 96 channels, you know, if you start turning up the system and you put the first one on, you know, the minute you're going to make any disruptions, even though the other 95 are not turned on, it's going to impact that one. So that has to be kept in mind. As I mentioned, wavelength specific components in the system. So if there's any deviation from a center wavelength, for instance, that can pose us challenges. And this is simply because of the type of passive components used. They use very precise filtering, pass-throughs, and band passes and band blocks. So this is why it can be a little bit complicated or not complicated, can be a little bit tricky and needs to be managed. Okay, and that brings me to the extreme closed channel spacing that we mentioned before as well. So a very little variation can mean a lot. Okay, and of course the metro challenges of 100 gigabits per second on top using the transport layer. So where would we start with testing these types of networks? Okay, and I always go back to the basics and what to test first. Our recommendation is always to test the connectors. We had a study done some time ago. This was done between VIAVI, back then JDSU, and NTT in Japan. And so these were the results. Basically, the connector cleanliness and the condition of those connectors will always be the number one cause of concern or cause of failure, right? So any dirty, any damaged, any improper mated connections, they will create major network issues. And if it might not happen straight away, you might have contamination that needs to be burnt in, depending as well on the laser power levels there. It may take a little bit of time, and I've seen on the for instance on the DAA technologies, they use very high power lasers, and they literally burn through particles on the connectors, which then of course stop the network. So that's number one. And for that, we have a mantra. It's called the IBYC. So it stands for inspect before you connect. So our regimen is to recommend everyone to inspect. If it is clean, then you connect connectors together. If it's not, you clean, and then you inspect again. And if we follow this process, there will be a lot better results, I can assure you. So what to test next? So one of the benefits of DWDM is that you can run multiple wavelengths over the same fiber. From a testing standpoint, if you use a traditional OTDR, what will happen is your OTDR will probably run on 1310 or 1550 or I don't know 1490 or 1625, and what will happen with the muxes and dmuxes is that as soon as they see that wavelength, they will block them, because it is not the wavelength that they are designed to pass through. So DWDM has very specific wavelengths that it uses, and these are set by your ITUT standards. And for such networks, there are specialized OTDRs. So we have DWDM OTDRs that will allow to run through the specific ITUT wavelengths. And here, as you can see, we have a tunable C-band OTDR that runs from channel 12 to channel 62, and it comes with a patented technology as well called WaveScan. So WaveScan allows the user to basically connect the OTDR to a port, and it will self-detect what that port wavelength is. And I'll give you an example of why that it is important as well. So there's been cases where you have DWDM ports which are labeled with their wavelength, and they may have been labeled incorrectly or mislabeled. And what happens is you can connect a DWDM OTDR, say, on the red port in the diagram down below, right? And the label says that it's a red port. Okay, so it's got a specific wavelength. So you set that wavelength on your DWDM, you shoot a trace, and nothing returns. So you get a, I don't know, you run maybe 20 meters and you get a break. And so you think, okay, there must be a break, or maybe the DWDM multiplexer is damaged. So there's been cases where these DWDMs have been mislabeled, and that's exactly what will happen. That doesn't mean that there's anything wrong with the physical components. It's a simple fact of a port has been mislabeled. So if you had to scan through all the channels on your OTDR, you will eventually find which color that port really holds. And that can be a very time-consuming task, right? So VIAVI came up with a technology that will scan through all the tunable DWDM OTDR capacity, and it will self-detect which channel that port is actually set to. And I think we have an example, yes, which is this one here. So here we're talking about a specific issue where this port was not passing light, right? And sure enough, when we developed the technology WaveScan, we've saved a lot of time for many technicians out there. So this could take a significant amount of time. With WaveScan, we can detect the proper channel in under 10 seconds. Okay, what else? What else to test? So definitely the wavelengths and the power levels are very important. So here we've labeled the different types of things to look out for in the different areas of the network. So there's areas where the transmit verification of the wavelength, the power, and as I mentioned, the drift is vital. We'll talk about drift in the next slide or so, because this is a very real problem as well that we are facing, and we have developed a fix for it as well. There is also the verification, as you would for fiber qualification, the insertion loss. So here we have to talk about the insertion loss per channel. So there could be a different insertion loss for the different channel wavelengths as well. So it's important that this is done, and it's done properly using the right tools, because the real fact is that these channels have different endpoints in the network architecture. So they have a common path in the middle, but on the fringes they could all end up with different lengths and different network events, like splices or connectors or what have you. So the insertion loss per channel is very important here. Of course, the continuity testing in the different areas and ensuring that there is the correct channel presence, as we mentioned. There's an importance to test also the total power levels, so the combined power levels of all the wavelengths, especially if there is longer distances, and especially if there are amplifiers which can be clipped if different channels are turned on. So that's very important as well. The actual Dmax and multiplexer testing, again, at a component level, these internally go through different paths through the filtering. So there is an insertion loss requirement, test requirement as well within these components. And final and probably the most important, because it's one of the key issues that we are facing or operators are facing, is the actual SFPs. Okay, so one of the we actually have a slide on this, so I won't talk too much about it here. Okay, so when selecting the right power meters for Dwdms, we are probably very familiar with the broadband power meter, and probably we all have one. However, you have to be careful when and where a broadband power meter is used. Okay, so a broadband power meter is used when it is used. It's measuring the average peak power of all the wavelengths present. So you've got a photodiode, and this photodiode is sensitive to all the wavelengths that is present on a fiber. It doesn't discriminate between these channels, especially since they're very narrowly close together on the same spectrum, right? So this will not provide an accurate power measurement if only one wavelength is present, right? So it's important that we keep this in mind because this can create different. It can give us different results, and we might be thinking that we're measuring one thing when in fact it's different. So there are power meters which are specific to these type of networks. We have a few flavors of them. There we find we call them channel checkers. Okay, so typically for the core you'd probably be using an OSA. However, in the access networks, you know, where you have perhaps there will be a number of technicians running these types of tests, and to keep costs in check, and also to reduce the complexity of using tools, channel checker will be good enough, because it will cover the main things that need to be covered. So it's got the ability, first of all, to isolate through the different filtering and measure each individual wavelength that you want to focus on. So this verifies your power levels and also the channel presence. And it also therefore verifies that your muxes and demuxes are in good operation, and also verifies that the correct channels and the power levels are reaching the right level at destination. We have two types. We have a standalone one, and then we have also a modular. The standalone is more compact, more pocket type. Of course, you know, if you go with a modular, you get something with a bigger screen, a little bit more feature add, and as we will see, it offers some other capabilities related to this topic. So before I mentioned about drift perhaps, or channel offset, and this is a very important thing to cover, because it's important to know how well centered your channel is, and the reason is that we have filters or the band passes and band blocks of in DWDM components. So here we're seeing an offsetted channel which is away from its center. So as you can see, the filter will chop that part out, so you're losing virtually that power out of your channel. And of course, this is going to create power level instability. So we have on our channel checkers, we have capability to test the power level over time as well. So here we're going with the number of sweeps, and as you can see, we have a drift in the power level as it changes over time. Okay. So I mentioned the SFP being quite an industry problem at the moment, and we do have our optical channel checker here that also has an SFP cage, so you can test SFPs on board the OCC module, right? So for instance, there was a problem where the network was unable to receive channel 28, and you know, technicians were guessing, okay, what's the problem? Is it a bad mux? Is it a bad fiber? Was it a bad port, or maybe a bad SFP? And a very simple test, basically pulling out the SFP, plugging it into our optical channel checker. Here is a zoomed closer image of our of the SFP, showing that it is set for channel 28. Okay, so it transmits at channel 28. However, when plugged in and when we ran a test on it, here it's showing that the ITUT channel is actually channel 29 that it's transmitting. So these errors can happen. There can be mislabeling of the actual SFP from what it was designed to do. And probably there's nothing wrong with the SFP. It's just that the label on it was incorrect. So this could be picked up very quickly, very easily with the optical channel checker, and that resolved that issue quite quickly. So this is not just VIAVI's view. The challenges are there with different SFPs. So here there was a survey done by Heavy Reading, and if you're interested in this survey report 2020, do contact Vicom, and they can share this with you. It's got a very interesting read. It's a very thorough study on different technologies for the telcos. So an extract from this, there was a question in the survey, and that read, with rising adoption of DWDM in access networks, what is the biggest challenge your company is encountering with DWDM? So there were 117 respondents. And as you can see here, the top one was a faulty SFP, SFP plus, where it could have been offset or a channel drift or mislabeled or an incorrect SFP altogether, right? So here there were 30.8% that responded that this is their #1 problem. So there you go. Okay, so that wraps up a little bit on the different test types on DWDM networks and some of our recommendations for DWDMs used in the access network. I just wanted to touch on a couple of things which are common to our platforms. So all of our platforms do support remote access. These times where people need to be a little bit more isolated than usual from each other. We have capability built into the platforms where these platforms can be driven through our own cloud, the Smart Access Anywhere cloud. So we make the remoting into these instruments very seamless. So there's no requirements for IP setting or any of the challenges that sometimes it takes to connect onto peripherals. So here we just put in a code that is generated by the system. It's very secure, and off you go. One other item that I wanted to mention is that, of course, all of this testing takes time. Time is money, OPEX money. And here now we are developing a lot of different automations to help with reducing that time. So we have cases where we've been able to tap into 50% improvements, for instance, in fiber construction processes by automating and simplifying and removing human error out of certain test processes. If you're interested in any additional resources, there's some links here and some posters which you can download or you can request for a hard copy. There's some product briefs and white papers as well on the different topics regarding WDM networks and some of their use cases. And that is it from my end. Chris?
Thanks, Matt. So very interesting and informative, Matt, especially I thought the overview of the modern DWDM applications and of course the subtleties of testing challenges. That brings us to the end of today's webinar, everyone. Please email us with your feedback on how we did and whether we met your expectations. And we'd also like to hear from you about any other topics you might want us to cover in future. As I said at the beginning, a link to this recording of this session will be available within a day or two. So if there's anybody in your organization that's missed out and would like the link, just let us know. And of course, if you've got any further questions or perhaps you'd like to discuss Vicom and VIAVI's DWDM or other optical and data test solutions, please contact Raj or Wallace, and you've got their contact details on the bottom of your invitation. So thanks again, everybody. We'll sign off now.